So we now try to understand why this works. Okay, so we will focus on simple problem. Okay, so you want to do this. For this particular problem, we do not have larger than 0. So you see, there's nothing here. We solve this. These are classical setup, not talking about the detail. Okay, then here's the thing. If step size fulfill this funny thing, then gradient descent converge. Okay, we talk about it in the next 3 page. And this 3 page is the detail. Okay, let's go to them one by one. Okay, I have this. Gradient is this. So now let's do gradient descent. Because gradient is yellow, this yellow become this yellow. Okay, x, okay, good. TQX, so TQX subtract and subtract become addition. So I have, this is I times x. So I have x take out, I have this plus TP stay here. So now I have this one. Now what's next? Now I'm here. So now I get this one. Now I have Q is what? Q is lambda. The eigenvalue of all the Q here, I call it lambda. And the VV, the eigenvector. So V, a bunch of lambda, okay, V transpose. Of course, it's smaller than VV. All of them are lambda 1. This is what I mean. And if you replace all the eigenvalue by the smallest one, you will get this part. Okay, so this is the idea. And what is this thing? This is the largest eigenvalue. Okay, if I now call this thing mu, then I have this. Then what? So now I'm going to get this one. This one is exactly this thing. So we have this one. Now I put a negative sign. I flip this two. So L go to here, mu go to here with a negative sign. Okay. Now I just factor out the I. The norm this is smaller than norm this. So I have here. Okay. Again, I have number times matrix. So this is what? This is AM. Norm is smaller than absolute A, norm M. Okay. Absolute is important. Okay. Then I have this one, the second line. Like this is just 1. So gone. So I have this thing is something. Okay, something below A larger than B, then something is below max of these two. Okay, these are in absolute value. Be careful. So I have this. Now what we have this thing smaller than red box is bounded above and below by another 2 red box which give me this. So this thing is bounded by this thing times this thing. Okay, so that's why you have this. I can then what? This one apply again. So I have another big bracket. And then I have this one, another big bracket again. So I keep going on. Then I will have all this max term, product. So this, I get this. This is initial starting point to the solution, which is a number. So if I can prove these things are all smaller than 1, the distance of my x to the solution is 0 in the end. So I just need to make sure this is true. This is true if what? At all the iteration, this thing is smaller than 1 means both of them are smaller than 1. So this is what I have, and this translates to this thing. So I have 2 cases, right? The second thing is this thing. Okay, I have these 2, right? So because of time, I skip the detail. So now I have this. I want this to be smaller than 1. This is what I want. And then blah, 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 blah. High school math, you get this one. So now you see why we have the 1 over L. This is why you have step size 1 over L. You remember the picture? I have a point here. I build a quadratic upper bound. This thing is symmetric. So 2 over L actually means you move to here. This is whole thing is 2 over L. So half supposedly, because this thing is symmetric, let me draw better. This is 1 over L. So here, supposedly, you should go this amount. This is exactly 1 over L. This is another 1 over L. If you go this amount, you jump to here. It's not minimized of this guy. You may argue, no, if I jump to here, this is good, this go down further. No, because you are only seeing this thing. You don't see this thing. You only know this is better. If you know this thing in below, you already solve the problem, okay? So that's why you usually pick half of this. So that's for each one of the step size, or the t. Same for the beta, not for the mu, okay? So now we have this. So if I want to solve this is the convergence. And for the convergence to be true, I want the t to be like this. And what is the step size? Anything between 0 and 2 over L. The constant step size, we use 1 over L. It works. That means 1.1 L also works. Okay, let's see. Now, I have the same code. I didn't change anything, right? Now, I only change the black thing. Wait, the black one is this one. Remember? Right? So, the original step size is this, right? Let's run it. Okay, this is the black one. This one, okay? Black one. Working, right? Now, what if I change this to 1.99? Not 2, right? The black should go down. Yes, still go down. Yeah. But what happens if I change to 2.0001? In this case, it just still keep going down, but sometimes it go up, okay? Yeah, if you see sometimes it go up, okay? But if you do it, this, it always go down, okay? 1.9, okay? This always goes down. And if you really want to see, if you do, yeah, it never have something go up, you see, never. So that's the idea. Because if you make it smaller than 2, this thing always smaller than 1, then of course go down, okay? Now, this is the idea. Why we pick this step size 1 over L? Because this is the best. So suppose I have this, and if I pick this is 1 over L, then this thing become L over L, 0, okay? This thing is mu over L, okay? This one is 0, we don't care. Max with 0 is something, always the number, so we get this thing. Kappa is exactly 1 over, is the L over mu, okay? So I have this thing, is the conditional number of the quadratic term. It means how you pose is a very good pose problem. You have a circle. It's just one step, you go to the solution. What about this thing? What are these? These are the A here, right? And if you remember, what are these things? The conditional number of this thing are exactly the eigenvalue of the largest one divided by the smallest one. And this one is very ill conditioned. So that's why you have a 1 minus something, kappa, and this gives you something like 0.8 k. So it decreases slow. But this one you need more iteration. And this one is perfect, it's 0. Good. So this is the idea. Okay, so therefore, this is the idea. So suppose kappa is 1, you have 0. That's why you converge in one step. But if kappa is 99999, so that means basically you almost see parallel line, okay? Then your algorithm will be what? Will be like this. That's why it's very slow in this direction. And that's why if you do Nesterov acceleration, you cancel out this kind of thing. You focus more on going here, of course it's faster. And it basically don't converge, okay? This theorem is for what? Quadratic function. But this theorem also is true for general f. If the f is L smooth. Yes, this is the funny thing. So this is another thing. Now here's the thing. You may not know this. Actually, 1 over L is not the best. What's the best? This is the best. 2 divided by the largest eigenvalue plus the smallest eigenvalue. Compared with this, you have this expression. Here, you have this expression. And what's the difference? If kappa is 2, you have this versus this. And then what's next? Summarize. I have this. And I also have this one means you have 2. If the problem is cheap to compute eigen decomposition, this actually is better. But if it's not cheap, just do this one. Okay? What's next? Then now we need to prove why it converges fast. Here's the idea. This is the first time you see this Polish name. So what's this? Again, we solve this. So let's recap. We have L smooth. Okay, you remember L smooth is what? So a function convex f is L smooth if there's a cone here. In other words, you don't have this. You cannot have this. Okay, this is 90 degrees. This means very fast change. Small L means what? The largest possible slope, the size is bounded. So you cannot have this kind of crazy sudden jump. Okay, this is impossible. Okay, right? If you have this change, can you draw a quadratic function on top of you? Here, yes, but what about here? No. So therefore, you cannot draw a quadratic function on top of you. So therefore, this one is not okay. Then I have this. This means what? This is my f below. This is what? This thing, right? So you have a quadratic on top of you. Okay? Then detail. Not going to prove it. The figure. Okay? Then now we have this thing. What is this? This is the easier version. So what is this? Let me give you some background. This one, Polish, saying that here's the idea. You have a point and then you move. Okay? So this. The idea is what's the length of this curve of then what is this? How long is this thing? Is this what? Is what? It's integrate this on t, dt for t in the right? So this is the idea, right? Now what are we doing? We are doing optimization. So we don't have this, okay? But we have d something d1, okay? Then we don't care about the one, okay? Then what? Well, of course you can say this is my t. I put it here. It's fine, okay? Then what? I want to find the length of this. Here is integrate. Now we don't have this integration. This is discrete. So we want to find a length. So we find the length by this. What? Xk plus 1 minus xk, right? And we run from iteration, let's say 0 to infinity. Then this is what? This is the length of this thing. Here's the idea. This algorithm converge if this is, right? You remember? That's why I talked about it in day 1 or lecture 1. I have a sequence ak converge to a something. I call it a star when k go to infinity. Okay? This is the same as I have a partial sum. I call it s, k, no sk, let me call it s, r. Okay? This is sum of k equal 1 to r, a, k. So, what is this? This is like A0, A1, A2, A3, A whatever, okay? A infinity, okay? What's this is my S2, this is my S3, this is my S4, right? The idea is I want to prove limit of sequence. I can prove limit of series, okay? This is sum all of them. This is series. If this thing converge, okay, converge, that means what? That means this thing converge to S something, which is not positive infinity. Then it implies A star, that means where A converge is 0. So this is the analysis thing, or you can think of, which is integration, right? You remember, integration exists if this thing go to 0. What is converge, right? That's it. So that's the idea how you prove converge. And this idea is basically, okay, and then basically make it for gradient descent. So this is like 70 years ago. Okay, I don't know what is this, maybe 100 years ago. Okay, so this is the idea. So you need this, what is this? The gradient of f, the norm, that means how big is the slope at what? At a particular x, and x can be any x for what? This x in DOM f. That means, this means what? This means x can be infinite far away from your f star, your x star. Or even x is x star, that means x is pseudo, then I have this. Here's a funny thing. But if my x is not x star, I still have this. This is a measure of optimality condition in terms of gradient. This is what? This is a measure of optimality condition in terms of function value. Do you remember? Okay, I talked about it. Okay, let me try to find, do I have that? Yeah, here. F minus f something. Okay, I can put it fx. Okay, it actually this one. If I know my f star, then this is the same as f minus f star smaller. And the gradient norm is this one, right? So basically, the PL is linking the zero convergence to the first order convergence. It's a way to link of them. Okay. So now jump. So this is convergence on function value. That means you don't know where is the x. You just know the fx. This means what? This is the slope. That means you still don't know where is x. You just know the gradient of f. What I'm saying is this true, then this converge. This is what? This is x, not fx, not greater than fx. This is the variable. So I now have three things. Number one, the gap between f and the best f. Number two, how big is my gradient? Number three, the x itself. I have three things. This thing is saying that this is true, then I can use this argument to prove convergence. That's the idea. And historically, this is true for something called algebraic function. That means you can take derivative, okay? So now let's go to the idea. And once you realize it, it's crazy. The proof is crazy simple. Yeah, this is the proof. Done. Yeah, gradient descent, very difficult proof. No, done. This is the proof. Yeah. So what's that? I have this. What is this? F Lipschitz gradient. I have this. This is the quadratic function upper bound picture, right? And I need this, right? Because I am assuming I do gradient descent, of course I can compute gradient. So this is basically telling me for all the gradient I compute in gradient descent, how big is the gradient? There will be a L, that this is true. Okay, this is number one. Number two, what is this? Gradient descent update. This is definition. There's nothing changed. This is no explanation. Now what I'm going to do? Okay, I put this y equal x plus 1 and put x equal xk. So let's do this. So this is xk plus 1. So I put a plus here. This is, I put a plus here. Okay, this I put a plus here. Okay, this is just x. So this is x, this is x. Now what? What is this? Xk plus 1 minus xk. That means this thing minus this thing. So this term give me, right, there will be a 1 over L. There's a square, so I take it out, so 1 over L square. But the L square cancel with the L, so I have this. Okay, number one. Let me do it one by one. Okay, so I will have fx plus smaller than fx plus, just copy the thing, gradient fx, x plus minus L. So this part is this thing. So minus 1 over L gradient. This part is L divided by 2. This whole thing square, that means I don't care about negative, so I have 1 over L gradient. Okay, now I have this. So what's next? I just simplify. So once I have L divided by 2, there is a 1 over L here, but there's a square, so I will have 1 over L square norms of F. Okay, these two terms are the same thing, but this one will have what? We'll have, this one is gone, this one is gone. This is what? Minus 1 version of this thing. This is plus half version of this thing. So I will have this. Okay. So now I have this. What is this? This is saying that new value smaller than old value subtract something. So this is fxk plus 1 smaller than fxk minus 1 over 2L gradient. This equation is very important. This is called sufficient descent. This actually is one of the key things to prove something called palm converge. So what does it mean? It means I have a function that looks like this. This is my fk. Okay. Suppose I move to this point. This is my xk plus 1. This is my fxk plus 1. And this gap is decided by how big is my gradient at the current moment. And if this thing is 0, gradient is 0 means x reached x solution, then new point equal old point makes sense because at solution, I shouldn't move. Yes. And also, this is mean what? Shouldn't move at the y-axis. The x-axis is if my gradient is 0, then this term is 0, then I don't move. Step size is non-zero, but this gradient is 0, so I don't move. Okay, right? Now go back here. So now I have this thing. PL inequality is just norm of gradient larger than something. Now I have a minus sign. So I just put a minus sign in the whole thing. So I have this thing. Oh my gosh, this is black magic. Now what? I just replace this red part by this red part. I get this thing. What is this? I subtract f star here. This part is this part here. The f minus f star is here. Then this whole thing inside is also f minus f star. So I have this. Now you see the same conclusion. I have the 1 minus 1 over kappa here, but now in an f sense. Previously I have the x, right? Now I have an f. So that means it's the same conclusion. The convergence. I have the same convergence. Again, let me go back. Do you remember this? What is this? This thing smaller than, for some number, ratio, let me call it delta. Then you stop. This is one stopping condition. Okay? So, okay, these are remarks not important, but I talk about it a little bit. We have discussed, we use step size 1 over L. What happens if I do exact step size? By definition, exact step size is using the best step size. Of course, we have this inequality. Then everything holds true because you are doing better. Okay, so no change. The reason why people do the L1 over L is just because now you should know why people love 1 over L. Because this makes the algorithm very easy to understand, very easy to study. What happens if I don't do 1 over L? Okay, now imagine, now I have an alpha here, and now I have alpha here. And this alpha is the arc mean of alpha of something else. Then little bit more complicated. Okay, this is the, but if you know this, that this is always below this, then if I achieve something like this for the constant step size, if I use the even better step size, of course I go down more. So the whole idea holds true. Okay, and this is assuming what? Function convex and smooth. What about if it's strongly convex? You can go even further. Okay, no time. Now, okay, even more complete nonsense. Okay, these are other convergence criteria. So you can do this. This is what I just said, right? This is what? This is this thing. Okay, then you can do this. You have a number called this definition is called convergence ratio. So what is this? This exactly, you will remember the slope, this kind of thing. This is the idea, the slope. This is the slope, okay? And then you want this number to be what? As close as 0 as possible. That means very fast. And what is quadratic? Quadratic, you put a square here. Normally, nobody can get quadratic, so forget about it, okay? And then you can also do this and do this. So how do you stop an algorithm? This is about how do you stop an algorithm. Yeah. This is stupid in the sense that because this does not disregard the possibility you are at local minimum, or also maybe because your algorithm actually has something wrong. So this is the stupidest one, but easiest to understand. If you want a more complete one, you should use these, but very complicated, okay? So this is what I'm saying. The slope here is different, okay? And now I'm telling you the slope actually have an order. So what I'm saying is, remember this thing? This is the step size. If you use this funny step size, you get this number. And now I'm telling you, if you do Nesterov acceleration, you put a square root here. So what the heck? If you put a square root here, now you see, you have a kappa is 2, so now I have 2. Then I have 2 divided by 3, so I convergence 1/3. But the 2 here, then this is 1.1414, this is 2.4 something. 2 divided by 2.4 something is a very close to 0.7 something. So this one subtract is this. Now you see, this is almost half of this. And if you run what? 4 iterations, this is the number. This thing go from 1/3 to 0.11 to 0.13 and 0.001. Look at this thing. In 2 steps, it reached as far as 4 steps. So that's why you have one of these, another one is like this. Actually, this. So in 2 steps, you need 4 steps. So that's why you have this kind of crazy thing. This one is like you have 200 steps, but for this one, it just needs 20 steps. Yeah, this is 1/5 of 100. So something like that. Yeah, it's how we talk about why this is true for general F. Okay. So again, same thing, no change. But to make the discussion easier, I assume B is 0. If B is not 0, you just translate everything along B to make it 0. So we don't really care about what's B. Now here's the even more complicated thing, but let's follow me one by one. It's not hard, okay? So I want to minimize this. Now there's no P because P is A transpose B and B is 0. So P is 0, okay? Then now let's start. So I have this. What's this? Gradient descent. 1 over L gradient is Qx minus P, right? But there's no P. And then what is the next derivative? Okay, you can think of this like this. I'm using X to update Y, and I'm using Y to update X, but I have this funny thing. Now I want to make them in one line. So this is X, right? So what I'm going to do is, this is Y. I have this thing, go to here, and go to here. And this is the previous version. So this big thing is this thing. And then there's a beta here. I keep it, okay? So now I have this very long expression. Then what I'm going to do, I just simplify. This is xk, this is xk, this is xk. So I just jump to here. I group everything have xk together. And then there's also, so this are detail. No time to talk about detail. So now I have this. Now Q is positive because Q is A transpose A. A is full rank, so this guy is full rank. Full rank have eigen decomposition, so V lambda V. Identity matrix is just V lambda VV. Because VV, I can always write identity as this. So Q is V lambda V. Now what's next? I have, this is the same as what? You will remember, V is eigenbasis. Multiplying eigenbasis means I rotate the coordinate along the eigenbasis. So I am doing coordinate transform. But still, it keeps everything. I have this V, this V go to the right side, I have nothing left. And then the V go to here. And why I'm doing this? Because if I move this to the other side, now you can see I have something V transpose something, V transpose something, V transpose something. I rename this V transpose something as W. So I have W plus 1, WK, and W previous one. I just want to remove all the eigenvector. So this is coordinate transform. Nothing changed. I keep all the algorithm, not changed. Because the algorithm is step size, 1 over L, and the natural acceleration parameter beta. So therefore, I'm just converting the algorithm into no V. Okay? Now what is this? Identity matrix is just 1, 1, 1, 1, 1, 1, 1. What is this? 1 over L, lambda 1, lambda 2, lambda 3, lambda 4. You see my point? This thing scale with this number on this only. So I have successfully decoupled everything into component-wise. So each component only care about the own variable. And what is this? Second order ODE, right? This looks like second order ODE. At time k plus 1 is my current time minus something previous. This is where people observe this and ODE thing. But this is not ODE, but finite difference equation. So I have this, then what? This to here is just math, simplify the terms. Now, then I have, this is second order ODE. Then characteristic equation, what's that? The root of the coefficient, blah, blah, blah. Then I have this thing, and then if you solve the characteristic equation for this on beta, that means the quadratic function, you get this expression. For those who are familiar with second order ODE, you should be familiar with this thing. This is what? This is the dynamics of ODE. And you have this characteristic response, you know, you have these three things. 1, you never stop, but converge very slowly. 2, you oscillate and then slightly getting smaller, smaller, and smaller. 3, you stop at the fastest time. These are the three things possible in the second order ODE, right? Now here's the magic. Magically, next drop is the one that is the fastest one in ODE. So this is the analysis by you turn it into a second order differential equation. So everything connected. So some people try to explain why next drop is fast because it's doing the fastest critical dam in terms of second order ODE. And this is why it's like this. Now, here's the thing. This is a second order ODE, right? And you know for a second order ODE, you can always write the solution as some psi cosine thing, right? This is the solution of the psi cosine thing. And this explains why there's a psi cosine thing here. So this is why you have this ripple. It's a wave. This explains why you run fast. And then the coefficient inside, okay, these are just ODE thing. I'm not going to talk about detail. You can solve it. And it's square root kappa. That means the conditional number of the function determine this thing. The conditional number of this is what? The radius of this thing versus the radius of this thing, right? These two things divide each other, give you conditional number, right? This one, very bad because this one is very short. So the conditional number is very big. This one is not. So it's saying that if the conditional number, this thing, is very bad, this actually is about the frequency of this thing. Why? Because why we have going up? It's because we overshoot. And this overshoot is actually caused by what? Caused by we going too much. Why going too much? Because natural expression, the parameter didn't know you should not go too much. It's still an estimate. The frequency of this, which is coming from the geometry of this. So therefore, that means what? You can actually predict when should you restart. So this is restart, right? You can actually know where you should restart if you know this frequency because of the second order ODE. So there's an algorithm called adaptive restart. Is that every time it's like this. It's like I run next iteration for 7 steps. At every 8 step, I stop and run one gradient, and then I run again. So then you will ask, how do I get this number 8? you calculate the frequency of this dynamics by using the second order interpretation of Nesterov accelerator. Then you will get this funny thing. Yeah, the frequency is something like this. You may wonder, how do you get this? Oh, this is just second order ODE thing. So because you have a x dot dot plus a x dot plus bx equals 0, then you guess the solution is in the form of a, e, this, and then you plug it in, solve this using initial condition. Then in the end, you get something like this, and then it cycles. Yeah, then you get this. Okay, that's the idea. So now, if we are in ODE, then why not we talk about ODE? Now let's talk about ODE. So this is the general form. We have this. Okay, remember I have the -1 here. -1 in the start. I don't run Nesterov. I just make it go down. So this is the Nesterov accelerator. This is called Paul-Sine parameter because it's simple. And this is not the Nesterov parameter many years ago. That's a bunch of alpha, beta. Okay, simple one makes another easy. So we know that we have this convergence. Now I'm going to show you this funny thing. This thing derived by 3 people, Su, Boy, Kendall, say 2017 or 16, I don't remember. The magic is there's a 3 here. Okay, now let's talk about this. So let's do the step one by one. So I have this is Nesterov accelerator gradient and nothing new. What I'm going to do is I want to combine them into one. So let's look at it one by one. So this thing, again, have y. I don't want to see y, I want to only see x. So I try my best to remove y or I remove x. So I first have this. What is this? Is this part, or is this part? Just replace this by this. Then now I have this. Then I move this guy to the other side. Then I have the thing here. This is crazy. Usually you say, oh, I divide by t, divide by t. No, it won't work. You need to divide by square root t. This is not trivial. So this part is important. You divide by this. So in other words, the condition is that the continuous time are quite tough. Okay, confusing. T is step size, not time. Okay, and the discrete step size k is related by square. It's not continuous time divided by step size is discrete time. It's continuous time divided by square root of step size give you time. So this is the tricky part. This one is people find. The biggest contribution of the paper 2017 is to discover the square root thing. Technically, it's just the square root thing. After the square root thing, the math is just simple. Okay, then now what? So because of this, big means continuous time. Okay, so my big X in terms of time is discrete time k times the gap or the increment square root t, and I'm saying this is approximately xk. Small means discrete, big means continuous. Now what if this means you have one particular step more, right? ak plus 1 means you have the time plus 1 small time. Then this will be this thing. Now I want to make this inequality become equality by taking, this is not time, repeat, this is step size, just confusing notation. So xk plus 1 minus xk divided by what? Step size, this is not time. Okay, let me repeat, this step size will be this one and this one. So that means what? That means if I put a limit, I will have equal. Okay, but now I didn't put limit yet. Okay, so this is the idea. I have this thing, and later on I want to make this is dx dt after I take the limit. Okay, so this is okay, right? So this is the finite difference. Then what's next? Now let's recap what's Taylor series for ODE. So for u, x plus small change is blah 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 blah. Okay, we assume everything is differentiable. Okay, then we can have this. Now u is big X, so my dynamics is on variable x. My small x0 is time. The small time. This tau is time. The small change is delta x, that is square root t. Again, not time. This is step size, right? I have this thing, which is this whole thing, but this one go to here, and then divide by square root t. So now, in other words, this part, which is this here. So now I have this funny thing. This is what? This is plus 1. I can do the same thing on minus delta x, right? So backward. So if I do backward, I will have minus here, then I get this. There's a square, so we don't care, but okay, this is plus, I forgot. Okay, so now we have another ODE. So we have first one and a second one. This one, I do the same thing here. Be careful about the minus sign. Then I get this one. So now this one. Why I need these two? I want to cancel term. I want to cancel something in the middle that I don't like. This is the big reason. So now I have this thing, and I also have this thing. So this is the thing. So now I have these two terms. Okay. And now, these two terms, what are the things in common? One is minus. This is the dot dot. This is the small ot. So what I want to do is, I combine them. How do I combine them? So this thing go to here. Now I have this funny thing. This part is cheating. It's not real mathematics. I just assume they are the same in the long run. This, if we want to do what transient analysis, this is wrong. But steady state analysis, this is okay. Then I'm assuming in asymptotically time, in the long run they are the same. So x is y, so this is just x, right? So this whole thing now become this. This is not correct for transient. That means if your focus is in the very beginning, which is the most complicated thing in ODE analysis, this is wrong. But for us, optimization, we consider in the end, so we don't care. What's this? Now, too many symbol. I hide the tau, so I have this. Remaining step is to kill this guy. Then we have here, we cannot take this limit go to 0 because this will die. So no, we cannot do that. So we need to make sure a very tricky thing. Okay. Then this thing is this, just math. And for long run, k bigger than, we don't care about the 2. So we have this. And since k and tau is divided like this, so I can replace this by this tau. Now you see why there's a magic tree here. I have this thing. So now this whole expression is this thing plus 1. So there's a 2 minus this thing, and there's a minus term, so I have this. So therefore, all the beta term replaced by this kind of funny free thing with a square root t. Now I have a second order gradient form. The second order dynamics plus the first order dynamics times 3 divided by tau time, okay, plus the gradient equals 0. So this is the ODE. Now what to do? You use the convergence analysis for ODE, you will get this. Therefore, discrete time Nesterov acceleration is a special case of this ODE. Therefore, you also have this. The difference is, if you do the optimization analysis, you can tell what is this C. But now since you use ODE analysis, you don't know what is this C, you just say there's a C. It's fine, we don't care constant, we just care about the behavior. So that's the idea. So this is how you prove Nesterov converge 1 over k squared using ODE.